Hey guys, welcome to this video on the single machine total tardiness problem. On this video we're going to first discuss the essence of the problem, how we're going to formulate it as a mathematical programming model, and then we're going to learn how we can use Python and Pyomo, an open source framework for mathematical programming, to find the optimal solution of this problem. But first, let's describe the problem. Let's describe what is the single machine total tardiness problem about. Now, if you are a student, you might be familiarized with this project. Imagine that you have a bunch of essays or group projects that you have to finish by the end of the semester. You have different deadlines and you have different durations for each one of these works. For you, it's important to determine, okay, what is the sequence of execution of these different group projects and essays so that I minimize the number of total penalty days. That means the number of days that I go beyond the different deadlines, because most likely you're going to have a penalty in case you go beyond these deadlines. Now, to familiarize yourself with this problem, I created this short video game that you can all play and you can access. The link for this small video game is going to be in the description below. But let's look at this little video game. In this one, we have only one construction crew that is in charge of building different buildings. We need to each one of the buildings is going to have a duration. That's the amount of days it's going to take to build it, and it's going to have a deadline noted by dt. This, for example, in this first building we have auto A and we have to finish it by day 32, and it takes 9 days to finish. So if I place it on the first sequence, we're going to finish it on day 9 and there's not going to be any delay because, we're far beyond 32. Now, for us, since we only have one crew, we need to determine the sequence. So we might go and we might do this. For instance, auto D in the 4th position, E, F, G. And to spice it up, let's invert these two ones. Let's put J in the 9th position and I in the 10th position. And this is going to result in 268 days. So if we look here and we look at the results, where we're going to be paying a lot of penalties, so we have a lot of penalty to pay. So we go ahead and we might try again. So we might now try, I don't know, this sequence B, A, D. Let's start crossing them around. F here, E here, and so on until we finish. And this one produces 260 instead of 268, 260. So we look at the results and we're still paying a lot of penalty, but this one is better. And we might try again and again and again for different combinations. In fact, when you start realizing how many different possibilities of sequencing these 10 hotels we have, you're gonna realize that, okay, you have actually around 3,600,000 different possibilities to sequence these hotels. And we want to find the optimal one, the one that minimizes the number of total days of delays. So, just randomly trying, it's not gonna work, and let me explain you why. So let me explain you why by going through these slides. Let's simplify it. Instead of 10 hotels, let's say we only have 5. Again, our job is to find the sequence. So let's try to determine how many different possibilities do we have. If we try to schedule the first one, the first hotel in the first position, which one? How many different possibilities of choices do we have here? Well, we can put A or B, C, D, and E. We have all of the potential hotels. So we have 5. But once we choose the first one, for the next one, how many possibilities do we have? Well, we have chosen 1, so for the next one it's only 4. And for the next one is 3, and for the next one is 2, and for the next one is 1. But how many different possibilities? Well, in total is the multiplication of all of these numbers, which actually is the factorial of the number of hotels that we have to scale. So this is a problem that its complexity, its computational complexity, how difficult it is to solve, it's related to the factorial of the number of jobs or hotels that we have to scale. And as you might know, that factorial growth is huge, it's horrible in fact. If you go on the right side and you try to compute the different factorial of integer numbers, once you're already at 20, we are starting to talk about the realm of what a supercomputer might compute. And this is what we know as the combinatorial explosion. The amount of possibilities is so huge that it gets out of possibilities really fast. Okay. Already when we are talking about 100 hotels, the amount of possibilities for sequencing that is so massive that not even the fastest supercomputer can compute all of the possibilities, at least not in this brute force approach, like enumerating all of the possibilities. So we need to figure out a smarter way, and that's what we're going to try to do in this video. We're going to try to formulate this problem in mathematical programming form so that a solver can help us. So let's start by defining the variables. What are going to be our variables? Well, we're going to start with our xj variables. These xj variables, we're going to have one variable per hotel or activity or job that we want to sequence, and in the x variables we're going to store the start date of each one of the activities. This is what we want the mathematical the solver to find. Okay, so xj's are going to be integer variables because they are going to store the start date. But we're also going to have these past due variables. These variables are also going to be integer numbers. We're going to have one variable per hotel or job, and it's going to store the amount of penalty days that we are going to have given a start date. That means if I have a hotel that has to be finished on day 10 and I finish it on day 12, well, the past due variable for that hotel is going to contain the number 2 because it has 2 days of delay. And finally, we're also going to have some binary variables, and we're going to have one binary variable per combination that we can produce from the list of hotels or activities or jobs in our problem. As an example, let's imagine that we have A, B, and C. Well, how many different combinations I can make with these 3 indexes? Well, only 3. We can produce A and B, A and C, and B and C. So we're going to have one binary variable per combination. So what is our objective here? What do we want to achieve? Well, we want to minimize the total number of past due days. It means we want to minimize the total number of penalty days, the accumulation. Okay, good. That's pretty clear. What are going to be your constraints? Well, the first constraint is the one that is going to allow me to compute the number of penalty days for an activity, but the penalty days, if an activity doesn't have any penalty days because it finishes before the due date, I want this number to be 0. If the finish date of an activity goes beyond the deadline, I want to have a positive number. So we need a sort of if condition here, and this is achieved by this constraint here. So we have here on the left side the start date of an activity plus the duration. The duration is an input parameter. We have that in a data table. So the sum of these two quantities is the finish date, and the finish date has to be less than the due date, the deadline of an activity, and the amount of past due days. Okay, it always has to be less than that. To illustrate how this works, let's look at an example. Let's imagine that we have an activity that is started on day 5. It has a duration of 3, so that means that it's finishing on day 8, and it has a deadline of 10. So this activity is finishing before the deadline. So the PJ is going to be 0. Why is going to be 0? Because the model is going to try to minimize the sum of all of these PJs, and in this case, since it doesn't have a due date, this constraint, and this is not violating the deadline, this constraint is going to be valid for PJ equal to 0. So the model is going to set it up as 0. In contrast, let's look at another example. We also have, again, the start date at 5, the duration of 3, but now the deadline is 6. So if we put these numbers in this constraint, we're going to see that if we set up PJ equal to 0, this constraint is not valid anymore. So PJ has to be equal to the amount of past due days, which in this case is 2. Okay? So by putting this constraint, we are enforcing the condition that if an activity is finishing before the due date, then PJ for that activity is going to be 0. If it's finishing after the deadline, PJ is going to be equal to 2. So then finally we have we're going to have to set up on our constraint, and this constraint is the one that is going to allow us to tell the model that only one activity can be executed at the same time. Okay, so So this is going to be working like a binary switch, okay? So this binary switch is going to allow us to do this. If I have an activity, if I have two activities, I have to make the choice of starting with A and then proceed with B, or start with B and then proceed with A. Okay, only one of these choices can be accomplished because there is only one crew to execute the activities. So we can only work in one activity at a time. So how we're going to do this? Well, thanks to our binary variables and an additional trick, a big number that we're going to call big M, we're going to be able to accomplish this OR condition. Now, big number n, like how big it should be? Well, it should be at least bigger than the sum of all of the durations of the activities in this problem. Okay, at least it has to be bigger than that. So how this is gonna work? Well, with big M on our binary variables, we're gonna establish these two equations, this pair of equations. So for each one of my binary variables of the combination, we're going to produce a pair of equations, and we're going to set up these two constraints. And with these two constraints, we're going to be able to achieve this OR condition. Let's see why. So we have our two pairs of equations. Now, what happens if the binary variable AB is equal to 1? Well, if it's equal to 1, then this top one, this binary variable, is going to be equal to 1. So this first equation is going to be reduced to this, okay? And since big M is bigger than all of the durations of my project, it doesn't matter how I set up A and B, this constraint is always going to be valid, okay? Because M is such a big number that this right hand side is always going to be bigger than the start date plus the duration. So we're in essence making this first equation irrelevant, okay? It's always going to be valid, doesn't matter the numbers that we choose. But for the second one, if we replace the binary number with 1, this is going to be equal to 0, and now we're enforcing that the start date of B plus the duration must be less than or equal to the start date of A. So we're enforcing the model to start first with B, and once B is finishing, then proceed with the job or activity A. So if the binary variable is equal to 1, then only equation 2 is going to be enforced and equation 1 is going to be irrelevant. In contrast, if the binary variable is equal to 0, then now equation 1 is going to be the relevant one. We're going to force the model to start with A and then proceed with B, and the second equation now is going to be irrelevant because it doesn't matter the values of P, X, B, and XA, it's always going to be valid. Okay, so this works like a binary switch. Okay, it's either one possibility or the other one, and that's thanks to the binary variables and big M. On the next video, we're going to proceed to formulate this in Python and Pyomo. And please note that all the code and the link for the video game is going to be on the description below. Thank you, and I will see you on the next video.